Hello everyone. Today we're going to discuss plate tectonics. All right, and here are some things you need to know about plate tectonics, a little bit of history, um, and the importance of plate tectonics in paleontology and geology in general. All right, so let's do a little bit of history. The Earth has a lot of different features, and this is one of those ideas that this was done by heating and cooling events, and the end would be jagged mountains and some valleys and so forth. They had figured out that the Earth had rotated. The ground itself was believed to be static. And we have Alfred Wegener proposing the idea of continental drift back in 1911. The continents were once joined, and one continent in the past. This was supported by fossil record as well as the general shape of the continents. And here's one of the things where Alfred Wegener has supported. So looking at both South America and Africa, we find similar fossils in both of these areas. And if you look, it almost looks like this nice little puzzle piece that fits together. But hey, since we're dealing with paleontology, if we put these together just right, bear with me here for a minute, you merge these and you're going to get a dinosaur. So just having a little bit of fun. Here you go. There's your dinosaur. Don't know what you want to call it, but there it is. All right, so here are the fossils. We have a Mesosaurus, a Lystrosaurus, and a Cyanognithus. These are found throughout the southern continents, and the size of these creatures and the fact that only one of them is actually a halfway decent swimmer doesn't really make any sense unless the continents were once together at some point. So unfortunately for Wegener, his idea was rejected because there was no mechanism that he could identify that would move the land around. Remember, we're thinking that the land is still static. So he proposed that the continents were moving through the ocean floor, and this was rejected because it was impossible. It wasn't until the 1950s, nearly 40 years later, that we start studying other things like paleomagnetism, and this is showing that the Earth's magnetic pole has changed over time, and the only way for this to happen is for the ground to be moving. And we later find evidence of this in the seafloor in the Atlantic Ocean, and here's examples of that. So here we have a nice divergent boundary. This goes up through Iceland. This is called the Mid-Atlantic Ridge, and we have different periods of paleomagnetic normal and paleomagnetic reversals, and it's done in these nice stripes. All right, so we're looking for more evidence because we're scientists, so we want to find more and more data. So we start looking at volcanoes and earthquakes, and we're mapping this around the world, and for the most part they occur in very specific areas. So we start mapping these and we start finding the boundaries of what's going to become the basis for our plate tectonics. And here you see the mapping of those earthquakes and volcanoes and see where they fit. And this is actually a really good idea for where all these different plate boundaries are. Here you go. Here are the different plate boundaries that we have. You can see a number of them. The Pacific, the Cocos, this one's called the Juan de Fuca. And so we have quite a bit of them in different places. But just so you know that we do have these different plate boundaries. And along with paleomagnetism and getting our earthquake and volcanic data, we also have the fossil record, again supporting this idea that the continents were once together. But we do have an issue. We don't know definitively what is moving these plates. All right, so good idea, good hypothesis in theory moving forward is that there are convection currents beneath the Earth's crust that cause the plates to move, and this is the most widely accepted idea. So here's these convection currents. There's that mid-ocean ridge again. So the convection currents move in a specific way, and as they move, in this case, they're moving apart from each other, they will move the surface of what we stand on. Okay, and so there you see direction of which way the plates are going. And depending on where you're at, over here in Japan, we have them going in vastly different directions. So Japan experiences roughly at least one earthquake a day. You can see which direction these things are going. So parts of Africa are moving this way. We're getting further and further apart from Europe and Africa. And you can see kind of more or less the direction of how this goes. So here are different kinds of boundaries. You want to remember these. These are important. So we have a convergent boundary. This is an oceanic crust and a continental crust, and they're coming together. And we have volcanics that occur along with mountain ranges. A really good example of this would be in South America, where the Andes are. Another great example of a convergent boundary would be an ocean-ocean crust, where we have these wonderful island arcs. And a really good example of this would be in Hawaii. So again, that convergent boundary. We have one more convergent boundary. This is continent-continent. And in this case, our great example is the Himalayan mountains. Again, we're producing these wonderful mountain ranges right here. This is an ongoing thing in India. And the mountains in India, the Himalayas, gain about an inch a year, give or take. All right, so we have divergent boundaries. These are plates that are moving apart. Here's that wonderful mid-ocean ridge. The mid-Atlantic ridge is a fantastic example of that. And we have one more. So we have those convergence, we have those divergence, and we have one more, which is called a transform boundary. And these are plates that are sliding past each other. They're going to cause earthquakes, but they're not going to have any lava spewing from them like we do on the mid-ocean ridge or on our convergent boundaries with our ocean, and ocean continent. So here's your transform boundaries. A good place for those transform boundaries is in the Pacific and also the San Andreas Fault in California. So they're scratching past each other. They will move in this direction and they'll scrape against each other. Again, this is rough stuff, going to cause a lot of friction, and then the plates will snap together or snap back in their original position, and that's of course going to cause earthquakes and aftershocks. Now, the effects of plate tectonics are actually pretty big. So one of the things that will affect over a long period of time is climate. All right, so there are 5 factors that affect the climate. There's sunlight, and there's a nearness to a body of water, and there's the latitude that you're at, based north or south of the equator, and there's your elevation. All right, now also our topography, which is going to be hills and valleys, and so on and so forth. So looking at this, the only thing that plate tectonics is not going to affect is the sunlight. But given enough time, plate tectonics will change all of the others. So if you think about that example of how the continents were once together with Pangea, and then of course that separation happens, looking at the position of all these continents, they've changed drastically over time. There are definitely times in the history of Colorado where it has been underwater, above water. It's been dry. It's had all kinds of different things happen to it. It's been closer to the equator, further away from the equator, mountains, no mountains, and all of these different things have been affected. Nearness to body water, latitude, elevation, and topography. So all of these things have been affected by plate tectonics, and as we'll see, that plate tectonics provides the environment, and that environment then becomes crucial for what kind of dinosaurs we see later, because the environment is one of the things that's going to drive the evolution of these dinosaurs as well. So there is a quick tutorial on plate tectonics, and we'll come back and do something else in the future.